Before we get started here, yeah, it's 1:10. We can get started. But I mean, before we start with the math, let me just show you all real quick. So if you look at the Co-17C, your actual 17C class. If you ever missed class, you can go to the media gallery over here and you can watch the class video. Oh, look, the new one's up even. So there's the one from today, which I haven't seen yet. And then you can press play. You can make it full screen. Ooh, that's loud. And then if he's doing stuff on the board, you obviously want this view. But if he's doing stuff over here on his computer, then there's something you can do. I usually can figure out what it is. There's some way of like interchanging what's going. Oh yeah, I think we can. Oh, thank you. Yes, I always forget where it is. So you can interchange which thing is bigger. So if what's going on is happening on his computer, you can make that larger and see it more nicely. So that's definitely great to do if you've missed it, or you just want to go see something that you might be like, why did he do that? What was happening there? Also, and this is something I certainly use all the time because I'm just trying to see what's happening in the class. I like to turn it on to double speed or sometimes 1.5 speed because I'm just trying to see what he's done really quickly. So I'm watching it fast, but you might not want to, or you might want to slow it down if you get to a part of like what's going on there. Yeah.
He also uses like the middle one left board.
It will scan and pan. Yeah. So definitely. So there was a part I was watching today where like he was doing something off on the right where he is now. And I was like, what's going, and eventually it did scan over. Sometimes it takes a minute. I think it's automated somehow. So yeah, it just detects kind of where he is. Cool. Let's talk about limits for a bit and we'll see if we can get some partial derivatives as well. Let me grab my notes and things. Yeah, notes and things. Oh, actually, before, yeah. Sorry, I had every time. Is this the right? Yeah, okay. Sorry, I'm always, I always grab a bunch of things and then I'm like, where did I put them? They're not. Just a moment, please. I thought I had more pages. I must have, you know what? I forgot to actually go grab them. That's fine. I'll live with what I've got. Okay, so. Some paper as well. Paper in here. Somewhere. Paper, yes. Cool. Every time. I'm forgetting things every time. Oh. Cool. So let's talk about some limits. So much like in 17A, if you're trying to find a limit, you're first going to try just to maybe plug it in. So for example, let's Co-17C today is the 12th. Yeah, the 12th. Let's say we want to find the limit x comma y approaches 1 comma 2 of x squared plus y squared minus 1 over x plus y. And before you do anything else, you should just try plugging in x equals 1 and y equals 2. And if you get a real number, that's pretty much the answer. And if we do that here, we're going to get 1 squared plus 2 squared minus 1 over 1 plus 2, which is, let's see, 5 minus 1 is 4 over 3. That's it. That's all there is to it if you get a nice not dividing by 0 situation. Much of the time, you're going to end up getting a division by 0 situation, which is fairly typical. So let's look at some examples that are a little more typical to come by, like the limit is x comma y approaches 3 comma 3 of x squared minus y squared over x minus y. In this case, if we try plugging it in, here's what happens. We get 9 minus 9 over 3 minus 3, which is 0 over 0. And as you may recall from 17A, you may not, when you have a 0 over 0 limit, that's what's typically referred to as an indeterminate form. Meaning the limit could end up having any value or it could end up being undefined, does not exist. So we have to do some work. And in this class, the work is often going to boil down to kind of one of three things. The most common situation, which actually is not going to occur here, is you're going to look at different paths. or different curves, and you're going to be getting two different values and the limit's not going to exist. Some of the time, like in this example, things will factor nicely. So here, I can rewrite this as the limit as x comma y approaches 3 comma 3. I factor the numerator as x minus y times x plus y divided by x minus y. X minus y divided by x minus y is 1. And now I want to point out, x minus y divided by x minus y is 1 as long as x minus y doesn't equal 0. But it doesn't because, right, we're not actually plugging in 3 comma 3. We're saying, well, we're getting really close to 3 comma 3. But that doesn't mean that x and y are necessarily the same. We're just getting close to a place where they happen to be the same. So as long as we're not actually there, which is what's happening in the limit, x minus y divided by x minus y is 1. So we can say we have the limit as x comma y approaches 3 comma 3 of now just x plus y, which is 3 plus 3, which is 6. So sometimes things work out nicely like this. Sometimes they don't. And I think this one was in your class, but I want to do it anyway because I want to show you some pictures. So if I was going to look at the limit as x comma y approaches 0 comma 0 of x squared minus y squared over x squared plus y squared. I do think you did this one in class, but it's sometimes it's worth repeating things because there's stuff I want to show you. So in this case, yeah, you could factor the numerator, but that's not particularly helpful. Right? Factoring the numerator as x minus y times x plus y doesn't really get us anything because the denominator does not factor. X squared plus y squared, you're just stuck with. There's no nice way of factoring that. So, and I see also if I plug in 0, 0, I'm going to get a 0 over 0. So again, some sort of indeterminate form. We've kind of put it in quotes because 0 divided by 0 isn't really an actual math thing. That's why there's like quotations around it, but you don't really need that. So in this case, what we start doing is we start looking at various paths that go through the point we're approaching. This tactic is most commonly used when you're going through the point 0, 0. Because it's really easy to identify paths that go through the point 0, 0. Like, for example, here are some of the paths we might use. Y equals 0, x equals 0, y equals x, y equals x squared, y equals a multiple of x equals y cubed. The list goes on, right? I could spend all day just listing out all the different paths. I mean, it would never end, right? There's literally an infinite number of paths that happen to go through the origin. But some common ones are x to the first, x to the second, x to any positive integer power, or y, or x equals y to any positive integer power. And then sometimes multiples of those things, like y equals 2x, or y equals 2x squared, or y equals 2x cubed. So usually you want to start with kind of the easiest or most basic choice you can. 0 is an often overlooked but excellent choice. So I'm going to pick y equal to 0. And when I do that, I'm going to set all of the y's equal to 0. What that means is when I write the limit, I'm just going to write the limit as x approaches 0, because y is already 0. I'm left with x squared minus 0 over x squared plus 0. Excuse me. I simplify, I get the limit as x goes to 0 of x squared divided by x squared. And now, as long as x isn't 0, let me ask you, in this limit, I know this is kind of a funky question, so don't worry about getting it right or wrong. In this limit, is x actually equal to 0? No. It's getting really, 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 really close to 0. But it's not actually ever getting to 0. The question we are asking or posing when we write down a limit like this is, what is this expression getting closer and closer and closer to as x is getting closer and closer to 0? Well, as long as x isn't 0, which it's not, x squared divided by x squared is what? 1, right? If it was 0, we'd have a problem, right? 0 squared divided by 0 squared is problematic. But close to 0 squared divided by the same number that's close to 0 squared is just the same thing divided by the same thing, which is 1. So here we're going to get the limit as x goes to 0 of 1, and the limit of a constant is a constant. On the other side of things, I could pick x equal to 0. Other side might not be the right way to say that. On a different path, we might pick x equal to 0. If we do that, we have the limit now as y goes to 0 because all the x's are just 0. And now we've got 0 minus y squared over 0 plus y squared. And negative y squared divided by y squared, as long as y isn't 0, which it certainly isn't, is just -1. And the limit as y goes to 0 of the constant -1 is just the constant -1. And this is the crux of why this limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared does not exist, because these are not the same. And once you have two different paths that give you two different values, that's enough to conclude that the limit we were looking at, limit as x, y goes to 0, 0 of x squared minus y squared over x squared plus y squared does not exist. Very similar to how in 17a, if the left-hand limit and the right-hand limit weren't the same value, then the limit didn't exist. It's just now, instead of there being two directions that you can approach the value from, there's an infinite number of directions you can approach the value from, because you can come at 0, 0 from any direction or any path that goes through it. Okay, let me show you graphically what's going on here, just because I think it's worth seeing at least once or twice. Where'd you go? Hiding things from myself. There we are. Let's see. In this one, x squared minus y squared over x squared plus y squared. Cool. There we go. So that surface looks like this. And you can see some funky stuff is going on at the origin. And if you want to actually see what's going on there along, well, let's actually look at our paths. So our first path was y equal to 0. And if you look at where the red surface is intersecting the blue plane, that is the path that you're approaching the origin along. So along this path, well, look, that path is really just some constant value. In fact, let's just point out that that path is the constant value of 1. Let me zoom in a bit. Ooh, I kind of zoomed in weirdly there. Let's go. Stop rotating. Okay. There we go. So along this path, along the curve, along the line and plane y equals 0, we're exactly just 1, 1, 1, 1, 1, 1, 1, 1 the whole time. On the other hand, if we look at x equal to 0, which is that plane, along that plane, we're now intersecting the surface down there. And if you look at the point -1, you can see, oh yeah, that surface definitely always has, I should say, where these two surfaces intersect is always a value of -1. So we can see, oh yeah, we're just -1 the whole time. And then we get really, really close to that point there, which although it doesn't actually exist, right? That point is not on the surface because you can't plug in 0, 0 to the surface and get a number, but it's approaching the value of -1. It just happens to be like removed right there. So from this direction, you're approaching -1. From this other direction, you're approaching +1. And so the limit can't exist because you've got very different values above and below. Kind of neat. Question? So when I say limit, I'm asking what value is the function getting closer and closer to as we approach the point we're talking about. In this case, the point being 0, 0. And in this case, the function isn't getting close to one specific value. It's just doing different things from different directions. On the other hand, just to kind of go back to the previous example we looked at, if you look for a second at, let me add in one here. How do I add it? Here we go. Yeah. If I look at, let me turn these off for a second. The first one we did, which was z equal to x squared minus y squared over x minus y, which is not going to look very interesting. There's a parentheses around this here. X squared minus y squared. Oops, you gotta be careful there. Divided by x minus y. Well, we know that when we do that, right, x squared minus y squared divided by x minus y is just x plus y. So, and this again, this looks kind of super funky, but there's your plane, z equals x minus y. And you can see that no matter which direction you approach the origin from, you're going to get your, I should say, which direction x, y approaches 0, 0, the z value is going to be getting closer and closer to 0. It doesn't matter if you come at it from the y equals 0 direction, which I would love with a different color right now, or the x equals 0 direction, or the y equals x direction, or the x equals y squared direction. All of those surfaces, when they intersect each other in this curve, are going to be going through the point 0, 0, 0. So the limit as xy approaches 0, 0 is the z value also being 0. Neat. Most, I would say most of the time when you're looking at limits in this class and they're going through the order, so xy is approaching 0, 0, it's a good bet that it's probably going to not exist. It's not always going to not exist, but I would always approach problems where the limit is, as xy approaches 0, 0, I would always approach them thinking it's probably not going to exist. I should start trying different paths to see what happens here. Let's look at a couple more examples. Yeah, let's look at that one. Don't think you did that one, class. I was watching it. Oh, in fact, I have them all over there. That's fine. Let's look at the limit as x, y approaches 0, 0 of 4xy over x squared plus y squared. Man, I don't love if you see that little camera thing up there on the screen, remind me to like click on it so it's not there, because I feel like it's a hindrance as far as viewing what's happening. Also, the mouse could probably not be there. That'd be great. All right. So again, I do a quick check. I say, oh, if I plug in 0, 0, I'm getting 0 over 0. So I know I need to look at some paths. I definitely think you should always consider at least one of either x equals 0 or y equals 0. Usually they are fruitful. Occasionally they don't help. Let's do x equals 0. So if x equals 0, then I'm left with the limit as as y, right? I said x was 0, so I'm left with y approaching 0 of 4 times 0 times y divided by 0 squared plus y squared. And let's be extra careful in our simplification here. 4 times 0 times y is 0. And the limit as y goes to 0 of 0 divided by 0 squared plus y squared. Now, it looks like we might get a 0 over 0, but it's a lie. Because before we evaluate the limit, we're going to simplify the expression. And specifically here, y is definitely not 0. It's some number that's not 0. Great. What's 0 divided by not 0? Right. 0 divided by 0 is a problem. 0 divided by not 0 is beautiful. It's 0. So this ends up being the limit as y approaches 0 of just 0, which is 0. Oh, that was very helpful. We're happy about that. So now, usually my goal in the next stage is to find a different path that gives me a different value, because I'm usually expecting that to happen. It's not always going to happen. But you should try at least 3 things before you give up. Probably more, but at least 3. I'm going to point out that if I tried y equal to 0, I would get the same result. If y was 0, I'd end up with 0 on top divided by x squared. 0 divided by x squared is still 0, and the limit of that would be 0. Yeah?
How come we don't just go with that and say the answer is limit is 0?
Because it's not. Because we're going to try some other paths that are going to show a different value.
I guess my question is more so with the other problems that we've done so far, we stopped right there. So I guess I would know if.
Yeah? Because I saw the ones he was doing in class, and it looked like, I mean, there were a couple examples where he didn't showing the limit was 0, but there were certainly a few where we tried different paths and you got the limit not existing. Like one value was 2, one value was -1, and so on and so forth. So
Maybe I'm wrong. It just
sure.
feels like, I guess, I'm just like, do we do all 3 of the problems like to trickle check every single time?
Well, so here's the thing. Here's the thing. For the limit to actually exist, the limit has to have that value, whatever value we found first, every time, no matter what path we pick. So you're not wrong to say that there are a lot of other paths where the value is going to be 0. I could check the path of y equal to 0. And if I did that, I would get the limit as x goes to 0 of 0 over x squared, which is 0. But that's not exhaustive. To really kind of do this exhaustively, you would impossibly have to check every single path that goes to the origin. And there is a lot of them. Y equals sine of x is the path that goes to the origin. Y equals x squared plus 3 plus 5. I don't know. I can make something up without getting off track here. There's too many things to check.
So to clarify, it looks like you have the answer. We keep trying different things.
Right, because so just here's what I'll say. You can't show the limit as a number just by checking paths. You have to resort to some other technique. And I'll say that's different than the first one we did where it existed, right? When we did this one over here, where the limit ended up being 6, that worked out fine because we were able to do some algebra that let us cancel some things. And then we were like, well, it's always going to be x plus y no matter what x and y are approaching. So then we just plug in the values here. But that's not something we can do here because, well, there's no algebra to do here. I can't cancel anything really. So I'm going to try another path. Let's try the path. And now here's my thought process a lot of the time. I'm trying to make a choice for y equals something or x equals something. I would love to be able to make a choice so that essentially all the powers in the numerator and all the powers in the denominator have the same highest number or the same number. So I'm going to pick the path y equal to x. Let's see what happens when I do that. And you can either replace x with y or y with x. You just have to choose. I would always make the choice to have x's instead of y's. So I'm going to write this as the limit as x goes to 0 of 4 times x over x squared plus x squared. Replacing every y with x. Now, let's see what happens. I'm going to write that as the limit as x goes to 0. On top, I have 4x squared. On the bottom, I have x squared plus x squared, which is 2x squared. And since x is not 0, 4x squared divided by 2x squared is just 2. This is going to be the limit as x approaches 0 of 2. And as we've seen a couple times now, the limit of a constant is just that constant. Doesn't matter what x can be approaching 17. The limit as x approaches 17 of 2 is still 2. And therein we see, oh, those aren't the same. So the limit doesn't exist. So we can say that the limit as xy approaches 0, I'm gonna write it down here. The limit as xy approaches 0, 0 of 4xy over x squared plus y squared does not exist. Two different paths gave us two different values. I don't think I had this one set up graphically, but let's go ahead and take a look at it anyway, because I think it is, I think it's really nice to see these things. So let's go ahead and delete this one here. And we had what, 4xy. I feel like I did do that one somewhere down here. Maybe not. Maybe I'm just lying to myself. 4xy divided by x squared plus y squared. Turn that off. So go away. Yeah. So here's our funky looking surface again. Kind of, I mean, they're neat looking surfaces, I would say. Like, it's always kind of cool to like, wow, we can graph stuff in 3 dimensions. And if we look at the path, well, let's see, we looked at the path x equals 0 and the path x equals 0. If you look at that, let's see. So if you look at that, you can see, oh, can you see? You can kind of see, it's hard to see, like they intersect each other right along that line right there. So yeah, we're getting closer and closer. Well, we are 0 the whole time, right? 0, 0, 0, 0, 0 the whole time. And then in the other path I picked, which was y equal to x. Oh, I turned off the wrong thing. Sorry. Sure. Blue, why would you also be blue? That's terrible. I know there's a way to do something about that. Maybe. Which button? Cogwheel. Is it hiding from me? Thank you. I see it. I see it. Thank you. Thank you. Thank you. I almost closed it all. It's been terrible. Let's go purple. Cool. So we can see, oh yeah, look, those are intersecting each other exactly in a line that has a value of 2. So when y equals x, and if we see where y equals x intersects our surface, it's always at a value of 2. Oh, that's cool. It just showed up like that. So yeah, the limit along that curve, along the path y equals x, the limit is 2. Or along the path x equals 0 and y equals 0, the limit is 0. Different values. Limit doesn't exist. It always feels disappointing. You're like, the limit doesn't exist again. Such is the way of things in this class a lot of the time. Let's look at, we'll look at one more not existing example, and then we'll talk about one that does. Yeah, of course, anytime.
To know which path to like choose them, so your discussion is always at least choose y equals 0 and x equals 0.
I would always use those because they almost always, they often give you that the limit is 0.
And then how would you then go out on like choosing the next?
Practice.
Okay.
Practice, practice, practice. I knew y equals x was going to be a good choice because I could see that when I did that, I was going to get x times x on top, which is x squared, and x squared plus x squared on the bottom. So I had x squareds on the top and x squareds on the bottom. Y equals x squared here would probably not have been a good choice. I don't know that for sure. In fact, let's take a look and see what would have happened if I picked y equal to x squared. It might have helped, it might not have. So I try y equals x squared, I have the limit as x approaches 0 of 4 times x squared is 4x cubed. X squared plus x squared squared is x squared plus x to the 4th. Typically, if you get something like this where the powers are not the same, your plan of attack is then to factor out the highest power of x from the denominator. The highest power that we can. So I'm going to factor out an x squared from the denominator. Take the limit as x goes to 0 of 4x cubed divided by x squared times 1 plus x squared. X cubed divided by x squared is just x. So I'm left with just an x on top. And now I have the limit as x goes to 0 of 4x over 1 plus x squared, which is going to be 4 times 0 over 1 plus 0, which is just 0. So it doesn't hurt, but it just gives me another 0, which I already had. So it doesn't help me show that it doesn't exist. So again, the answer to your question really is practice. Practice, practice, practice. You have to do the homework to learn the material. Okay, let's look at another. Let's look at one more over here. Yeah, I'm going to change that up a little bit. Let's say we want to find the limit as xy approaches 0, 0 of 8y cubed times x over y to the 6th plus 3x squared. Yeah, that's not terrible. I mean, it's kind of terrible. All right. What should I try first? Thank you. Awesome. That is definitely what I wanted. Or x equals 0 would have been just as equally good. Let's try y equals 0. So if I try y equals 0, well, in fact, you all try y equals 0. You're going to have the limit as x goes to 0 of something. I'll give you like 30 seconds. All right, let's see. So let's do, I'm going to show less work here. So if I plug in 0 for y, on the top I have 8 times 0 times x, which is 0. On the bottom I have 0 plus 3x squared, which is 3x squared. 0 divided by not 0 is 0. I do think it's worthwhile to write this step, right? You could just say it's 0, but I like to say it's the limit of 0, and then that's 0. So now we need another path. And I will point out picking x equals 0 will also yield 0 for the same reason. So I want something else. If I tried y equals x, I don't think it's going to help that much. If I try y equals x, I'm going to have the limit as x goes to 0 of 8 times x cubed times x is x to the 4th. On the bottom, I'd have x to the 6th plus 3x squared. If I factor out an x squared from the bottom, I have x squared times x to the 4th plus 3. In the numerator, I have 8. I'm going to break up the numerator just to make it easier. X squared times x squared. So that the x squared divided by x squared is just 1. And so then when I plug in 0 for the remaining x's, I get 8 times 0 on the top over 0 plus 3 on the bottom. My limit 0. It's nice, but doesn't, well, it doesn't help me if I think the limit doesn't exist. If on the other hand, I thought the limit was 0, I'd be like, great, this is proof that or more, not proof, but more evidence that my limit is actually what I think it is. I don't think the limit exists though. So I'm displeased by this choice of mine. So I'm gonna try something else. Anyone have a suggestion they want me to try? Yeah, y equals x cubed. And here's why that's a good choice, or maybe the best choice. If I plug in x, or actually, I might have made a mistake writing this problem. You're close to the right answer. That's a little further away, actually. So we actually need to go the other direction and say not y equals x cubed. So we do y equals x cubed, we're going to get x cubed cubed, which is x to the 9th times x. And then y, x to the 18th, whatever. What's the choice we actually have to make? Close. Not a square root, a cube root. Actually, not a cube root. Here's what I mean. We are very kind of... all of us like to mostly think about saying y equals some function of x. Y equals the cube root of x. Y equals x cubed. Y equals x squared. But don't limit yourself. No, the pun didn't work. Okay, fine. Fine. Don't limit yourself. Haha. You don't want to use roots typically if you can help it. Instead of using y equal to the cube root of x, cube both sides and use x equal to y cubed. It's usually, it's not so bad with odd roots. With even roots, you're kind of you're cutting off half of the path, right? If you do y equal to the square root of x, you don't get the bottom half as opposed to like doing x equals y squared. So pick the path that's more inclusive. So then we're going to do the limit as y goes to 0 of 8 times y cubed over y to the 6th plus 3 times y cubed squared. On the top, we have 8 times y to the 6th. On the bottom, we have y to the 6th plus 3 times y to the 6th, which is 4 times y to the 6th. 8y to the 6th divided by 4y to the 6th is 2, and the limit of 2 is 2. And so the limit doesn't exist. Okay. So what about one that is exist? Because occasionally you will see this. And there's a number of ways of kind of getting them to work, but there's a pretty common tactic that shows up in this class. So about the limit as xy approaches 0, 0 of, I really want that? That seems terrible. Let me make sure I'm looking at the right problem here. Let me just double check something before I send this off in a direction that might be awful. No, I guess that's fine. Okay, yeah, cool. We'll do it this way. Let's say we have, sorry, apologies. 2x squared times y over, I want to check one more thing really quickly. Oh, that's okay, yeah. Over 3x squared plus 4y squared. And I think some of the intuition I've seen over the years about this is, okay, this is not a great question, but it's all I've got. For lack of a better word, what's the degree in the denominator? What's the highest power of either x or y that's in the denominator? Right. Okay, now this next question is going to be the same, but the answer is harder to, I feel like, see. What's the quote unquote degree in the numerator? It's actually higher. It's actually higher. It's 3 because you have x squared times y to the first. And so we add those degrees together because you essentially have a third degree thing. It's just that y is acting like x kind of. So here's what I'm trying to say terribly. When the degree in the numerator happens to be strictly higher than the degree in the denominator, it often ends up being the case that the limit exists. Not always, but often. I don't really know why. It's just, well, I kind of know why, but it's something I've noticed over. It's really because your 0 is more zero-y on the top than it is in the bottom. So like your 0 in the numerator overpowers the 0 in the denominator, and you essentially get left with 0. Okay, great. So if I was doing this, I would start picking paths. So I pick the path, like y equal to 0. I'm gonna get the limit. X goes to 0 of 0 over 3x squared. We know that's going to be 0. Same thing would be true if I pick x equal to 0. I'd have the limit as y goes to 0 of 0 on top and 0 plus 4y squared on the bottom. That's going to be 0. Another path that might be nice to pick would be y equal to x. No, I don't think so, actually. Well, I'll try it anyway. It's always good to try things, even if you don't think it's going to work out. The limit is x goes to 0 of 2 times x squared times x is x cubed. 3x squared plus 4x squared. That ends up being the limit is x goes to 0 of 2x cubed over 7x squared. X cubed divided by x squared is x. So the limit as x goes to 0 of 2/7 times x, which is going to be 0. And then I might start suspecting that the limit exists. I'm like, oh, I mean, there's lots more things I could try. I don't really want to because I know the limit is 0. But there are lots of other things you could try. Right? Y equals x squared, y equals 2x. Oh, something people do sometimes, although I haven't seen your professor do this, but definitely the person who taught this last course did this all the time, is sometimes they like to be not exhaustive, but they like to say, I'm going to try every straight line that goes to the origin. Y equals mx, where m could be any real number. 1, 2, 3, 4, 5, pi, square root of 2, right? So you're basically saying, if I pick any line through the origin, is this going to existing every time, or am I going to get something that depends on m, which means a different slope would give me a different limit value, and then we're done. So if I tried this, the limit as x goes to 0 of 2 times x squared times mx over 3x squared plus 4mx squared. This ends up being the limit as x goes to 0 of 2mx cubed over 3x squared plus 4m squared x squared. And I can factor out an x squared from the denominator and get the limit as x goes to 0 of 2mx cubed over x squared times 3 plus 4m squared. And then x cubed divided by x squared is still x. So I get the limit as x goes to 0 of 2mx over 3 plus 4m squared. And if I plug in 0 for x, I get 0 on top, not 0 on the bottom. So that limit is 0. So for every line that goes to the origin, the limit is 0. Now I want to emphasize that is not every path. Right? There are lots of paths to the origin that are not straight lines. Parabola, any power function, right? Parabolas, cubics, et cetera, et cetera, et cetera. But this at least is even more evidence. Well, maybe the limit's 0. So let's go ahead and give this a shot. Let's write it again up here. Limit is x, y goes to 0, 0 of 2x squared y, 3x squared plus 4y squared. So what I would say here is this typically relies upon using the fact that x squared or y squared, depending on whichever thing you see in the numerator. So if you have an x squared and a y squared in the numerator, kind of pick one of them. But here I see x squared, and it's true that x squared is less than or equal to x squared plus y squared. Definitely true. Y squared is always greater than or equal to 0. So is x squared. So if you add this on, you can't be making it smaller. It might be the same, right? If y was 0, yeah, x squared would be equal to x squared plus 0. But if y is anything other than 0, whether it's positive or negative, this right-hand side is going to increase in size. And then I'll also point out that x squared is greater than or equal to 0. X squared is definitely bigger than or equal to 0 for any value of x, and less than or equal to x squared plus y squared for any value of x and y. Okay, and now here's what I'm going to try and do. I'm going to try and justify to myself that I can make this right-hand side into that denominator. So let's see here. Well, if x squared is less than or equal to x squared plus y squared, I can certainly multiply x squared by 3, and that won't make it smaller because it's not negative. So it's also true that x squared is less than or equal to 3 times x squared plus 4 times y squared. In fact, I could have maybe even written that as a more compounded inequality, right? I could have said x squared is less than or equal to x squared plus y squared, and x squared plus y squared is less than or equal to 3 times x squared plus 4 times y squared. That would have been a better way to do it then. I just didn't think about doing it better. Okay, but here's the real kind of fancy part. I'm going to divide everything by the thing that I want to be the denominator. So rewrite this as 0 divided by 3x squared plus 4y squared is less than or equal to x squared divided by 3x squared plus 4y squared is less than or equal to 3x squared plus 4y squared divided by 3x squared plus 4y squared. Okay. So now check this out. This expression here. Oh, I should let me do one more thing. Sorry. What's 0 divided by 3x squared plus 4y squared? Everybody. Thank you. And what's 3x squared plus 4y squared divided by 3x squared plus 4y squared? So the thing we're looking at here, x squared divided by 3x squared plus 4y squared, has to be between 0 and 1. No choice about it. Great. So now we're going to take that and we're going to use it in our limit. So I'm going to rewrite this limit so that the thing that I just talked about is kind of separated from everything else. So I'm going to rewrite this as the limit as xy goes to 0, 0 of x squared over 3x squared plus 4y squared times 2y. Right, that 2y is just separate. So here's what I'm actually going to say. I'm going to take this expression here. I'm going to multiply it all by 2y. That's a little dicey, James. Why is that dicey? Good question. It's dicey because y could be positive or negative. And if y was negative, you multiply an inequality by a negative, you have to switch the order of the inequality. So that's why it's slightly dicey. It's not really a big deal here, but sure. Yeah, now I feel like I've talked myself into a corner here. So yeah, what do I do? There's a way to deal with it. I know he did it in class too. Sure, we use an absolute value. So we're gonna say that seems just arbitrary though. Yeah, I don't love that. But it is true. Okay, here's something that's true that I don't love to have to kind of introduce, but if the limit of the absolute value of something is 0, then the limit of the something is 0. I'm gonna say that again. So let's this is something that is actually useful. So if the limit as x approaches whatever of the absolute value of f of x is equal to 0. Well, if the absolute value of something is getting closer and closer to 0, then the inside something had to be getting closer and closer to what? Could it have been anything other than 0? No. The only way the absolute value gets to be 0 is if the insides are equal to 0. That's not true for any other number, right? If this limit was 5, then the insides could have been getting closer and closer to 5 or getting closer and closer to -5. But 0 is kind of the special standout number when it comes to the absolute value. So if this is true, then it also has to be true that the limit as x approaches a of just the insides was also 0. So that's enough to say what I want to say, which is good. So here's what we're gonna do. We're going to say, I'm gonna slap some absolute values around everything here, which feels real fun. So we're gonna look at instead the limit as x, y approaches 0, 0 of the absolute value of all this stuff. Gosh, I'm getting really smeary over here. Sorry, I don't mean to be, but then my hand's just not moving the right way. I will point out x squared over 3x squared plus 4y squared is already always positive or non-negative. So it doesn't really need the absolute value, or the absolute value doesn't change anything about it. So I'm going to rewrite this as the limit as x, y approaches 0, 0 of x squared over 3x squared plus 4y squared outside of the absolute value, because it doesn't need to be inside of it, times the absolute value of 2y. By the way, just want to point out, from all this work we've done, you might see why most of the examples we look at end up not existing. Because showing one does exist is really a lot more effort. Doesn't mean you won't be asked to do that, it just means it'll happen less of the time. And so then here's what we're going to do. We're going to take this inequality and we're going to multiply every side of it by the absolute value of 2y. Here's what we've got. 0 times the absolute value of 2y is less than or equal to x squared over 3x squared plus 4y squared times the absolute value of 2y is less than or equal to 1 times the absolute value of 2y. And now we're going to use the squeeze theorem. 0 times the absolute value of 2y is just 0. 1 times the absolute value of 2y is just the absolute value of 2y. I'm going to ask all of you, what's the limit as y approaches 0 of, I should say x comma y approaches 0 comma 0 of 0? Everybody. Yeah. What's the limit as x, y approaches 0, 0 of the absolute value of 2y? Right, as y gets closer and closer to 0, 2 times y also gets closer to 0, and so does its absolute value. And then, since this middle thing is between those two things, and the limit of those two things is 0 on the left and 0 on the right, the squeeze theorem tells us that the limit of the middle thing has to also be 0. So by the squeeze theorem, or sandwich theorem if you like saying sandwich theorem, the limit is x, y approaches 0, 0 of x squared over 3x squared. Sorry, I know it's terrible looking. Apologize. Limit as x, y goes to 0, 0 of x squared over 3x squared plus 4y squared times the absolute value of 2y is equal to 0. And then I suppose we could say we should say one more thing, because we actually weren't looking at the absolute value. So then we can conclude that the limit as x, y goes to 0, 0 of the original thing, 2x squared times y without absolute values over 3x squared plus 4y squared is also equal to 0. It's a lot of work to show this limit exists and is equal to 0. This is a pretty standard way of doing it, though, is by showing that some part of your fraction is between 0 and 1, and then you can multiply it by some stuff, and the stuff you're multiplying it by ends up going to 0, so you show the whole thing is 0. It almost always ends up equaling 0. Not that it has to, but it's just pretty typical. Well, we didn't get to partial fractions, but we'll do that on Wednesday. Maggie. Oh, I thought you had a question, sorry. Yeah, sorry, that's all. So I will point out, there are older videos of me doing things. If you're looking for more information about partial fractions and stuff, you're certainly welcome to look at other stuff I posted on the YouTube channel that this class is for. So definitely look there if you want some partial fractions examples, or I say partial fractions, partial derivatives, not doing partial fractions. That was last quarter. Partial derivatives. If you're looking for partial derivative stuff, you can find those older videos on my YouTube channel, or you can wait till I see them. If you have homework you want to turn in, you're welcome to turn it in to me. I will grade it. He's definitely added problems to the homework assignment, right? There's 9.1, there's 9.1 again, there's 9.2. There's a lot of homework problems. I'm thinking it might make more sense for me to because grading all of this is probably a lot. I might focus more on grading just even ones, since those are the ones you don't have access to answers to. But certainly we'll cross that bridge once people start turning things in. So if you have stuff to turn in, turn it in. If you don't, that's fine. Turn it in next week. Maggie, I'm sorry. I keep feel like you're raising your hand. Okay, sorry. Maggie, no, okay. What's that? Yeah, of course. Yeah, digitally is great. Digitally or physically, whatever you like. I'm happy to take it any way you want.